Okay, hope you all can hear me well. I'd like to welcome you all to this technical session 13 of SIBGRAPI 2020. This session is entitled Datasets and Classifiers. We're going to have 3 papers being presented in this session. The first one, building datasets for rainforest deforestation detection through a citizen science project. The second one, fusion of BLAST and ensemble of classifiers for protein secondary structure prediction. And the last one is one-to-one large margin classifier. So I'd like to thank you all for joining this session, and I hope you can enjoy. So I'd like to start this session by inviting, the first presentation that will be given by Fernanda Jordan Rojas Dalacqua, building datasets for rainforest deforestation detection through a citizen science project.
Hi, my name is Fernanda Beatriz, and I will be presenting the work Building Datasets for Rainforest Deforestation Detection through a Citizen Science Project. Rainforests play an important role in the global ecosystem. Unfortunately, they suffer from indiscriminate deforestation. Therefore, monitoring programs are needed. One of the most known programs is INPS-PRODES, which carries annual Brazilian legal Amazon's deforestation survey by photo interpretation of Landsat 8 images. In April 2019, the Forest Arts project was launched at Zooniverse platform. It is composed by 5 modules, and in its Citizen Science module, the volunteers analyze and classify remote sensing segments. This work proposed to use these contributions to build efficient training sets through the new organization selection module. These training sets are used by machine learning techniques to detect deforestation in new remote sensing images. For the training sets, only forest and non-forest segments are considered. This work proposed to use the volunteers' contributions as training set. For that, 3 sets were built by taking into account the segments labels defined by the first 5, 11, and 15 volunteers from the Forest Eyes Masks League 2017 campaign. Other 2 sets were built with PRODES-based data to compare the results. First, it was defined the best band combination with hydraulic texture features. From 135 combinations, the combination of Landsat 8 bands 4 and 6 stood out. With this combination, the active learning was performed, where the baselines were supervised learning and random sampling. These baselines are compared with margin sampling with all the datasets built. After that, a sample visualization tool was performed in the datasets to check the separability between the classes. Random sampling achieved the worst results. MES-Zoo approach presented good results, where MES-Zoo 5 stood out, having outstanding non-forest accuracy, which is the target task of this work, detected as first deforestation in rainforests. These results demonstrate the volunteers' good cognitive skill to detect possible problematic tasks. By using active learning, it is possible to achieve similar or better results than supervised learning, but using fewer samples. With TSNE and linear SVM, it is possible to notice the better separability for zoo datasets, especially Zoo 5, maybe explaining why they achieved better results in the active learning experiment. Analyzing the campaign's answers, it was found that the first 5 volunteers to contribute to the campaign were volunteers that had some previous experience with forest eyes, while the other 10 volunteers were first-time volunteers. However, more investigation is needed to fully understand why Zoo 5 had outstanding results. This work shows that the Citizen Science module can be used to build high-confidence datasets. Active learning achieves similar or better results than supervised learning, but with fewer samples. The zoo datasets had good results, showing that the volunteers can detect noise samples that will be discarded by Forest Eyes organization selection module. Zoo 5 had the best results where, by using fewer volunteers' contributions to the Citizen Science module can be an even faster and cheaper procedure. However, deeper investigation is needed to check if this is a tendency. Finally, these results showed the feasibility of aligning citizen science with the active learning approach for the reinforced deforestation detection task. This procedure can be used to complement official monitoring programs or even generate data for areas where there aren't this kind of programs. For future, can be highlighted the use of different classifiers and active learning approaches. Also, all the information about the volunteers or the tasks could be used by the organization and selection module. The authors would like to thank the research funding agencies CAPES and CNPq. This research is part of the INCT of the Future Internet for Smart Cities, funded by CNPq, CAPES, and FAPESP. Also, thanks to the US Geological Survey for the Landsat imagery, INPE for produce data, the Zooniverse platform for hosting forest eyes, and its volunteers that made this study possible. Thank you.
I'm not sure if we have questions from the YouTube audience, but I have a question for you, Fernanda. I could not find from Huva as well any question, but I have a question. You mentioned in your presentation, that you were more or less trying to validate this kind of data coming and defined by volunteers, and you compare active learning with some other supervised approaches, okay?
Mm-hmm.
So one question is, when you mean active learning, do you mean that you relied on experiments with those volunteers as they are using the system in the kind of active learning, or the active learning experiment were performed with ideal volunteer?
The classifications came from volunteers that went into our platform at the Zooniverse platform of Forest Eyes. So they gave their classifications. So it's a real user. However, we first got all these labels and then emulated the active learning. So it's not like with the active learning gives use this, we need the classification of these samples, and then we sent to the citizen science module. No, we just emulated this cycle. In the future, the idea of this experiment was to emulate the cycle and see that it's viable, and then we can do it on the future. So we start with a seed, go to this and send these segments to be classified at the citizen science module. After that, we use that as training samples. And then the active learning, from this new data set, we need more these other samples to be classified, and then send this to the citizen science module, and then starts all the procedure. So in this first work, we had all the data labeled by the volunteers prior than doing the active learning.
I see. Okay, thank you very much. Congratulations, very nice work. I have one further question. I wonder, probably that can be found in the paper, but in your presentation you don't give much details about that. But I wonder if you could tell us a little bit about the volume of data that you have in those particular collections. How much data do you have? Yeah.
So for this experiment, we focused on detecting recent deforestation. So we used a mask to discard all the deforested areas that classified by PRODS prior than August 2016. So we used only the forest area, the supposed forest area from August 2016 to August 2017 to see where deforestation occurred on this date. So far, using the segmentation, the mask-slick segmentation, we had more than 4,000 segments. But to send 4,000 segments to the volunteers, it's very expensive. So for this experiment, we manually selected only 92 segments that had some pixels of non-forest areas, or deforested areas by prods, and a few other segments that had only forest pixels. So we manually selected only 92. But for future, the idea is we have a lot of segments to our disposal, but we need to intelligent select segments to be sent to volunteers. So it's a future work. Other campaign that we've sent all the images. So we sent like 1,000 segments to the volunteers, and the volunteers answered like in to 1 week of 15 volunteers answer all the tasks, all the 1,000 tasks in 1 week. And the other campaigns, they took more than 1 month and a half. So for future work, we need to see this, which amount of data to send to the volunteers to get fast responses.
Okay, very nice. Thank you very much again for your work and for the nice presentation. And look forward for the next step of the research. Thank you.
Thank you.
So I cannot see any further question for Fernanda, so we're gonna move to the next paper. So the next paper is fusion of BLAST and ensemble of classifiers for protein secondary structure prediction. This presentation will be given by Gabriel Oliveira.
Hi, my name is Gabriel Bianchini de Oliveira, and the title of this work is Fusion of BLAST and Ensemble of Classifiers for Protein Secondary Structure Prediction. The authors of the work are myself, Hélio Pedrini, and Zanoni Dias. Proteins are fundamental in biological process. They are formed by a sequence of amino acids which, due to the physical and chemical interactions between them, form three-dimensional structures. The local three-dimensional structure that each amino acid forms is called secondary structure. The classification of secondary structures is divided into key 3 and key 8 classification. The analysis of protein secondary structure is important to understand the global folding of the protein. In this work, we present and discuss a method using a fusion of global and local classifiers with BLAST. Our main contribution is to present a method that can predict protein secondary structure using the amino acid sequence, protein similarity information, and biological properties. Our method is divided into BLAST and an ensemble of classifiers. The fusion was performed using the bag of optimizers. BLAST is a tool for comparison of amino acid sequence of proteins, and it finds the best alignment. Using BLAST to find proteins with similar sequence alignment, some amino acids may not have a predicted secondary structure. With that, we employ the fusion with the ensemble of classifiers to predict all the cases. The ensemble of classifiers is divided into local and global classification. In the local classification, we used 5 different random forests with different sliding window sizes. The final prediction of the local classification is the fusion of the 5 different random forests. In the global classification of the ensemble of classifiers, we used 5 different bidirectional recurrent networks with GRU memory models. The final prediction is the fusion of the 5 different recurrent networks. The ensemble of classifiers is the fusion of the local and global classification. To perform the fusion of the set of local and global classifiers, as well as the fusion of the ensemble of classifiers with BLAST, we used the bag of optimizers. To evaluate our method, we used 3 different datasets: PDB, CB6133, and CB513. We evaluated the amino acid sequence and similarity information that are present on the datasets, and additional features, that is biological properties, distance, and statistical measures. To evaluate, we used precision and recall for 8 class and key 3 accuracy for the method. On the first experiment, we used the PDB for training and testing. The table presents the key 3 and key 8 accuracy of the method using ensemble of classifiers with additional features, BLAST, and the fusion of BLAST and ensemble of classifiers. On the second experiment, we used the CB6133 dataset for training and testing. The first table presents the K8 accuracy using the amino acid sequence and using the amino acid sequence and similarity information for ensemble of classifiers with additional features, BLAST, and the fusion of BLAST and ensemble of classifiers. The second table compares the results with the literature. The last experiment was training on CB6133 and testing on 513. The first table presents the results using the amino acid sequence and using the amino acid sequence and similarity information for ensemble of classifiers with additional features, BLAST, and the fusion of BLAST and ensemble of classifiers. The second table compared the results with the literature. As conclusions, protein secondary structure prediction has a major impact on protein folding. BLAST can achieve good results, but not can predict all the structures. Ensemble of classifiers can obtain competitive results compared to the literature, and the fusion can surpass the state of the art. The weights of the fusion between the ensemble of classifiers and BLAST show that the both of them helped in the prediction, and the use of sequence alignment and additional features of the amino acids can be a path for future work. Here are the acknowledgements, here are the references.
Okay, thank you, Gabriel, for the presentation. Very interesting work. So I could not identify. Let me see if you have questions. Yeah, I could not find the questions from online. I have a question. I'm not that familiar with this Q3 and Q8 accuracy. I wonder if you could, define those for us. Another thing is one key aspect when we combine different classifiers is to somehow take into account the complementarity of those classifiers. If they provide different results for different classes and so on. So for this part, I wonder if you have performed an analysis concerning the diversity of the classifiers. Thank you.
Thank you. The first question is about the key 3 and key 8 accuracy. The calculation of this metric is similar to the accuracy. It's equal to the accuracy, but the nomenclature of the metric is key 8 and key 3 accuracy. So we calculated the predicted values for the classes, and we calculate the correct predictions by the total number of structures. And the second question is about the local and global classification and the complementarity of them. Yeah, I'm right?
Yes.
Yes. Okay. It's important to get these two different classifications because the protein secondary structure prediction take into account the global interactions between amino acids. So close amino acids can form different structures depending on the close amino acids, and global structure prediction is important because far amino acids can interact between them and form a specific structure. So it's important to use these both classifications.
Okay. Okay, thank you for your answer. I cannot see questions from the audience so far. Any questions, Arlindo? No questions from YouTube? Okay, no questions. Okay, so I would like to thank you, Gabriel, for your work, and I look forward to seeing your dissertation at some moment in February. Okay, so keep the hard
Thank
work and thank you.
Thank you.
Okay, so let's move on now to the last presentation of this session. So I'd like to invite Jaime Laisa to present one-to-one large margin classifier. Thank you, Jaime. Nice to see you again.
Hi everyone, I am Jaime Roca. Today I'm going to talk about one-to-one large margin classifier. It is a joint work with Elio Pedrini and Ricardo Torres. Our motivation. The cross-entropy loss function is continually used along the time, especially for image classification. This loss maximizes the submax function shown in the equation 2. However, some works have pointed out several limitations, such as lack of representation power, propensity to overfitting, and misclassification caused by adversarial examples. In recent works, several alternatives have been proposed based on the large margin principle. It is, the classifier seeks for a model parameters that produce the larger distance between a sample and the decision boundary. In general, these approaches can be classified in two categories. In the first, the approach imposes margin on the top of the neural network. All these approaches provide margin, specifically at the submax function. In the second category, the approach impose margin not only in the output, but also in the input and hidden layers of the neural network. We propose a novel formulation that imposes margin at the output of the neural network. However, unlike the previous methods from this category, we don't focus on providing margin to the traditional submax function. Our approach has three components. First, based on the distance used for SVM to obtain maximal margin, we propose a broad distance definition called the one-to-n distance. In the binary classification setting, the one-to-n distance computes the difference between the distance given for one positive sample and all the negative samples. These distances are the distance from one sample to the hyperplane, defined by W and B. Secondly, we approximate a probability mapping function for the one-to-n distance. This is very different to the traditional submax function, because the one-to-n probability explores the samples in the mini-batch for its computation, instead of the hyperplanes for each individual sample as the traditional submax function. The last component of our formulation is a bound margin. We provide margin to the one-to-n probability function. Our goal is to gain generalization, imposing a margin and using the whole structure of the data in the mini-batch. We perform experiments over the MNIST, CIFAR10, and ImageNet Cherry2 datasets, showing that our approach has better generalization and noise label robustness than the cross-entropy, showing improvements in the following tasks: generalization robustness, robustness in noise label data, and robustness against adversarial examples attacks. Thanks for your attention.
Okay, thank you, Jaime, for your presentation. And thank you for the opportunity also for join this research path. So I have no questions from UVA software, UVA application. I don't know if Arlindo has any question from YouTube. Okay, so no question according to Arlindo. I have maybe now we can talk a little bit. I'm nice to see you again. So I wonder, yeah, very nice. Jaime, in the paper, you proposed a kind of validation in three different applications. Okay.
Yeah.
But of course, the impact of this kind of this kind of margin based classifier is huge in terms of the possibilities of using in different and challenging problems. So I wonder if you could elaborate a little bit about other possibilities of exploiting what you have proposed in other applications. So which other application would you like to try if this formulation could lead to better results?
The methods, for example, that propose large margin, but only impose margin at the softmax function, is very used in metric learning approach, and also in applications such as face verification and person identification. So our approach is easy to modify and adapt to these applications when the goal is to provide or improve representation to make when we obtain a well representation, we can find we can make search very easy, and this is that currently we are working to adapt this approach.
Okay, very, very nice. I like that you mentioned rain identification problem. Maybe you can still publish your masterwork. Okay,
Yeah.
so I have I have another question. One issue is the computational costs associated with the strategy proposed in this paper. I wonder if you could comment a little bit. Do you think that by modeling this distance to the negative samples, what is the overhead in terms of computational costs? Do you have any specific comment about that you could make?
Yeah, the difference between our implementation and the implementation that is used in gross entropy is a couple of operations, matrix operations, because we need to compute a lookup table that indicates the negative samples for each positive samples. So this is a difference in time, and also a difference in memory. But in our experiments, I don't see a significant difference in this computation. Yeah, this is only the difference, the computation on a lookup table.
I see. Okay, thank you very much again for your nice presentation and for the opportunity for join this work. Okay.
Thank you.
So I cannot see any further question from our channels of communications, YouTube, and also our app. So I would like to then close this session and thank you all for the nice presentation and for the opportunity to presentations. I would like also to thank those who have SIBGRAP 2020. So thank you all for joining us today, and look forward to seeing you at some moment in the future. See you. Bye bye. Thank you.